Ever wonder what goes on in the other side? The answer may shock you.
To get started with the topic so closely intertwined with math, you gotta have to know a wee bit of it. Alright, fine, vector calculus, but just the very basics. Let's get started with the definition of a vector. A vector is a quantity with both the direction and magnitude. In physics, we care about a particular type of vector called force. A force is simply a push or a pull in a particular direction. Gravitational force, electric force, magnetic force, yeah. But usually we don't care about just one particular vector. The world is full of vectors with all sorts of sizes pointed in all sorts of directions. That's why people have invented vector fields, a place where all these vectors can exist. Now that we have a bunch of vectors in one place, we can do math that models their behaviors. First, we have these curly d things. A normal d stands for differential or small change. Putting it next to a quantity then refers to a small change in that particular quantity. Dividing two differentials yields a rate of change. A common example of this is slope, where you can take the change in the y direction, divide it by the change in the x direction, and get a rate. The fact that these are curly doesn't really matter to us. That just gets into multivariable calculus and alphabet soup sadness. Then we have an upside down triangle with a dot. Called divergent, this operator has fancy vector calculus magic that goes on in the background, but really it measures how much the vector field points away from or towards a particular point. If the vector field is represented by a tub of water, divergence is the flow of water from one point to another. Dumping the water is a huge divergence, while dripping the water is a small divergence. Finally, the upside down triangles can be followed by an X. Curl! And again, pretending the fancy calculus doesn't exist, you can figure out what curl means just by looking at the definition of the word. Curling is rotation around a point, so curl measures exactly that in a vector field. Back to the water, swirling down a drain is an illustration of curl. Sign indicates direction of swirl, and magnitude indicates how swirly the water is. Phew, that's enough math for a day. Let's actually talk about the physics. In the 19th century, a physicist named James Clerk Maxwell stole a set of 4 equations from other physicists that he used to explain what happens when charges move. All that Maxwell did was modify one, list them, and take the credit. Sorry, Gauss, Faraday, and Ampere. The following image may be disturbing to some viewers. Wow, an array of calculus equations can be quite overwhelming. But let's look at each one individually. We already learned all the math. First, Gauss's law, where E is the electric field, rho is charge, and squiggly E sub 0 is some constant, we don't care. The divergence measures how strong the flow is from a point in the field. Greater charge, then, means greater flow. In diagrams, physicists draw lines to indicate the path of imaginary positive charge when placed in an electric field. Ha! That just goes to show how positive physicists are. A small charge will not have that many lines coming from it, as the flow of imaginary charges is relatively small. A large charge will have many lines, as the flow of imaginary charges increases. Gauss also takes the cake for the next law, his law of magnetism, which says that the divergence in a magnetic field is 0. While in an electric field there was an electric charge that created a measurable flow of imaginary positive charges, there is no magnetic charge that would cause the same flow. From grade school, magnets have a north and south pole. If the teacher allowed for kids to cut magnets into 2 pieces, the new magnets still work perfectly. No matter how many times you cut it, you always get new magnets with functioning north and south poles. This is an illustration of Gauss's law of magnetism. Magnetic charges can only be observed in groups, while electric charges sure can be single. Alright, new guy, new law. Faraday said that the curl of an electric field was equivalent to the rate of change of magnetic field compared to time. Imagine a coil of wire in a magnet. If the coil is moved through the magnetic field, the coil bumps into changing magnetic force lines all the time. And a movement in an electric field, from Gauss's law, can be represented as a movement of charge. This movement in charge has a fancy name, current. When the current moves through the coil, it swirls. Whoa, we just made electricity. Last one, Ampere's law. He related current and changing an electric field over time to the curl of a magnetic field. Again, for our purposes, we don't care about the difference between current and changing electric field. So, let's imagine a straight wire. If current travels through the wire, Ampere said that the magnetic field would curl around the wire. Wow, that was easy. So if we wrap the wire around a non-magnetic metal and apply the current, our metal is now magnetic. So in short, current, or a changing electric field, causes a magnetic field. On the other hand, a changing magnetic field causes a current. Alright, we just finished a brief introduction into electrodynamics. But why do we care? If some jerk named Maxwell and 3 other victimized physicists did not come up with their laws, we won't have any of this, these, those, and definitely not this. So these 4 laws have made much of the tech that we depend upon today possible. Ever wonder what could come next?